Look up at a commercial jet and then picture a satellite. It's like they were built in entirely different universes, right? Why is that? Today, we're stripping away the complex engineering to uncover the invisible, fundamental, physical laws down to the bouncing of microscopic molecules that dictate the designs of everything that flies. Let's get into it.
Think about airplanes over the last century. They generally all share that same basic, conventional shape. A long tube, wings, a tail. But spacecraft? Wildly different. You've got boxes wrapped in gold foil, giant metallic spiders, massive satellite dishes. There is absolutely no conventional shape for a spacecraft. The question is, why? Here's our roadmap for today. The anatomy of spacecraft, form follows the mission, researching the unknown, the two hands of nature, nature's perfect gas equation, and finally, the secret of consistent units. Section 1. The anatomy of spacecraft. Here's the thing. Even though spacecraft are designed to live in the dead vacuum of space, every single one of them has to survive a fiery, violent exit through our atmosphere first. That launch environment completely dictates a vehicle's anatomy. Take an expendable, multi-stage rocket, like the Delta booster. It's essentially 3 rockets stacked up, with the actual spacecraft hiding safely inside a fairing at the top. Once it clears the atmosphere, that fairing drops away, and none of the rocket is ever recovered. Contrast that brute force approach with the space shuttle, part space vehicle, part airplane. It rode strapped to a massive external tank and solid boosters, did the heavy lifting, and then glided back to land on a runway. Totally different launch anatomies driven by totally different economic and mission goals. Then you have completely out-of-the-box approaches, like the Pegasus rocket. Notice it actually has wings on its first stage. That's because Pegasus is air-launched. It gets dropped from an airplane high up, but still very much inside the sensible atmosphere, meaning the air is actually thick enough to push back. Those wings aren't for space. They're strictly there to generate lift and help boost the rocket higher before it hits the vacuum. The environment it launches in dictates its physical form. Section 2. Form follows the mission. But what happens the second we escape that sensible atmosphere? The rules completely change. Out in the vacuum of space, aerodynamic drag and lift just vanish. Poof, gone. This gives engineers the ultimate freedom to design a vehicle based purely on what the mission needs it to do. Look at the Mars Pathfinder lander. Its 1997 mission meant it had to unfold into a stable, flat base right on the Martian dirt so solar panels could catch the sun and a rover could roll off. Now compare that to Voyager 2, flying out in deep space for decades. It never needed to land. It just needed to fly past planets, so it was built with articulated instrument platforms, letting it point cameras precisely at planets like Neptune as it zipped by, no matter which way the main body was facing. Without air in the way, form purely follows mission. But you can't escape aerodynamics forever. To get that Pathfinder safely down to the Martian surface, engineers couldn't just drop the folded-up lander out of the sky. It had to be packed tight inside an aeroshell. That blunt, conical shape has one job: purposefully slam into the Martian atmosphere to create massive drag. That drag slows the vehicle down and acts as a shield, protecting the delicate instruments inside from the insane heat of atmospheric entry. Section 3, researching the unknown. This brings up a fascinating question. How do engineers actually know how to shape that aeroshell? How do they calculate the exact aerodynamic heating and drag a spacecraft will experience millions of miles away from Earth? Well, they rely on over a century of hardcore foundational research. We're talking decades of data, starting way back in 1915 with the founding of NACA, the National Advisory Committee for Aeronautics. Then, in 1957, Sputnik 1 launched, kicking off the space age, and NACA rapidly evolved into NASA. Every modern spacecraft design stands on the shoulders of the massive aerodynamic data archives built by these organizations. Section 4. The two hands of nature. Thanks to all that relentless research, we can actually strip away the overwhelming complexity of multi-stage rockets and interplanetary probes and look at the absolute first principles of aerodynamics. If you want to build your intuition, internalize this one incredibly powerful fact. It doesn't matter if it's a paper airplane or a hypersonic missile. Every single aerodynamic force, lift, drag, all of it, is caused by just 2 microscopic interactions between the gas and the vehicle's surface. Just 2. Number 1, pressure, which is a force pushing perpendicularly or straight down onto the surface. And number 2, shear stress, which is a friction force rubbing parallel along the surface. That is literally it. Think of pressure and shear stress as the two hands of nature.
picture nature physically reaching out to grab a spacecraft. One hand pushes straight down on the hull, that's pressure. The other hand slides and rubs across the hull, that's shear stress. When you are trying to understand lift or drag, all you're doing is adding up the pushes and rubs from those two invisible hands across the entire vehicle. For instance, when that blunt Pathfinder aeroshell drops through the Martian atmosphere, pressure is doing almost all the work. But if you look at the sleek, smooth wings of a commercial jet cruising at altitude, shear stress, friction, becomes a massive factor.
Section 5, Nature's Perfect Gas Equation.
Okay, so if pressure is one of nature's main hands pushing on a spacecraft, how do we calculate exactly how hard that hand pushes? To do that, we've got to zoom way, way in and look at the microscopic nature of the gas itself. To keep the math tethered to reality without needing a supercomputer, engineers use a brilliant model called the perfect gas. In real life, gas molecules have these tiny magnetic attractions to one another, but in a perfect gas model, we just pretend those sticky intermolecular forces don't exist. We simply picture the gas as a bunch of tiny, perfectly bouncy billiard balls zipping around and smashing into things. And this bouncing billiard ball idea gives us one of the absolute most important equations in aerospace: nature's equation of state. Lowercase p equals rho times r times t. Let's break this down into a physical story. P is pressure, the actual physical force of all those tiny bouncy balls smashing into the spacecraft's hull. Rho is density, literally just how tightly packed those balls are. R is the specific gas constant, which just depends on what kind of gas you're flying through, like Earth air versus Mars air. And T is temperature, which is simply a measure of how fast those balls are moving. Here is your mental heuristic to remember this forever. Pack 'em or heat 'em. If you pack more molecules into a tight space, increasing density, or if you heat them up so they fly around much faster, increasing temperature, they are going to smash into the hull harder and more often. The pressure, P, goes up directly. Let's do a quick sanity check. When a spacecraft re-enters the atmosphere, friction makes the gas temperature absolutely skyrocket. Looking at this equation, if T spikes, P has to spike too. The pressure on the aeroshell becomes immense. Now, a very common mistake people make here is forgetting that R changes depending on the planet. You absolutely cannot use the R value for Earth's nitrogen-rich air to calculate your landing on Mars, where the atmosphere is mostly carbon dioxide. If you do that, you're going to crash. The only time this perfect gas model really breaks down is in mind-bogglingly cold environments, or incredibly high pressures where those gas molecules get so squished together that you just can't ignore their sticky magnetic attractions anymore.
Section 6, the secret of consistent units. Now, having a beautiful, elegant equation like that is great, but there is a major trap that catches tons of beginners, and frankly, even seasoned engineers, and that's mixing up the units of measurement. You always want to use nature's equations in their pure physical form. Trying to shoehorn man-made conversion factors into a physics equation is just begging for a catastrophic calculation error. The ultimate secret safeguard here is to always use perfectly consistent unit systems. If your inputs are consistent, your outputs are mathematically guaranteed to match physical reality.
Whether you're working in the SI metric system or the English engineering system, you have to strictly memorize these consistent sets and stick to them. If you're using SI, force is newtons, mass is kilograms, length is meters, temperature is Kelvin. If you're in the English system, it's pounds for force, slugs for mass, yes, slugs, and feet for length. The single most common mistake beginners make is mixing up pounds mass with pounds force. Please don't do it. Treat these unit systems like completely isolated islands. Sticking rigidly to one system acts as a built-in mental safeguard. It ensures that when you calculate the pressure on a spacecraft, the final number on your calculator exactly matches the true physical force of those bouncing gas molecules in the real world.
We've journeyed all the way from the massive macroscopic anatomy of deep space probes right down to the microscopic forces of gas molecules and the elegant mathematical rules that tie it all together. So I want to leave you with a thought. Knowing that a spacecraft's form is completely liberated from aerodynamics and the vacuum of space, and that its shape is dictated entirely by its mission and these fundamental first principles, ask yourself this: what will the very next generation of spacecraft look like? When we finally push these equations to their absolute limits and build vehicles for interstellar travel, what radically bizarre, functional, and beautiful shapes are we going to create?